Welcome back to Basic Electronics. In this lecture, we will look at diode circuits involving a capacitor. As we will see, the presence of a capacitor adds a new dimension, and we will see how to analyze some of these circuits. We will first look at the peak detector circuit. We will then consider a clamper or a level shifter circuit in which the output waveform is a level shifted version of the input waveform. So let us begin. Let us consider this circuit with a diode and a capacitor. The configuration is fairly simple, just these two connected in series. But it's very different than the circuits we have considered so far, which had diodes and resistors. And let's take a look at in what way the circuit with a capacitor is very different than a circuit with diodes and resistors. For example, here is a diode circuit which we looked at earlier. Now for this circuit, in principle it was possible to take some value of Vi, figure out whether for that input voltage the diode D1 was conducting or not conducting, whether the diode D2 was conducting or not conducting, and then solve the KCL, KVL equations to figure out what the output voltage would be. And in fact, we could consider not just one Vi value, but a whole range of Vi values for which the diode D1 was on and D2 was off, for example, and then figure out what VO versus Vi would be for that particular range of values. Once we had considered all the possible cases, then we could plot VO versus Vi for this given input range. And having obtained this information, we could then proceed with plotting VO as a function of time for a given triangular input. And this was possible because all elements here are static. For example, for the resistor we have V equal to R times I, a static relationship. For this voltage source we have V equal to 1 volt, that is constant, again a static relationship. For this diode we have I versus V as given by this graph, again a static relationship, there is no time anywhere, and there was no dynamic element such as a capacitor. So when a capacitor is included, things become different, and that is what we will look at in the next slide. Coming back to our original circuit, we see that there is this capacitor which now introduces dynamic behavior in the circuit, because the capacitor current IC is C dVc dt. That's not a static relationship like V equal to IR. It's dynamic because the capacitor current depends not only on the present value of Vc, but also on what happened in the past, because it depends on the rate of change of Vc. So that's the complication, and we therefore need to consider how the capacitor is charging or discharging when we look at circuits like this which have capacitors. Okay, so let's get started with this particular example. We will assume that the diode is ideal. It has an on voltage of 0 volts. The capacitor voltage Vc is initially given to be 0. The input voltage given by this graph is applied, and we want to find VO as a function of time. And we assume that the diode is ideal. Its on resistance is 0 and off resistance is infinite. Let us redraw this circuit for two situations. One, the diode is conducting, so its resistance is R on. Second, the diode is not conducting and its resistance is R off. R on is very small, R off is very large. Okay, so let's look at the situation at t equal to 0. We have the input voltage equal to 0, the output voltage, which is the same as the capacitor voltage, also equal to 0. So the P end of the diode is at 0 volts, the N end is also at 0 volts. That is the situation at t equal to 0. Now the input voltage starts rising. The capacitor voltage is 0 volts at the beginning. So this N end of the diode is at 0 volts, and now this voltage is going up as the input voltage increases. So the diode turns on, starts conducting, and we have this circuit now coming into the picture. So the capacitor starts charging through the diode. And what is the time constant for this process? It's R on times C, which is very small because R on is a very small resistance, ideally 0. So the time constant for the charging process is a very small time, and much smaller than any of these times that we see in this graph. So in other words, the charging process is going to be instantaneous. So the capacitor voltage is simply going to follow the input voltage, and that is what we show over here in the pink color. Beyond this point, what happens? Now the capacitor voltage has reached 2 volts, and the input voltage has started dropping. So the N end of the diode is at 2 volts, and the P end is now going below 2 volts. As a result, the diode is now under reverse bias, and we are operating somewhere in this region. So the current is 0. The diode is replaced by resistance R off, which is very large, ideally infinite. And if the current is 0, then the capacitor voltage cannot change. So the capacitor voltage becomes constant at 2 volts, like that. And that continues right up to this point, because throughout this interval the P end of the diode is lower than the N end, which is at 2 volts. Now the input voltage starts rising above 2 volts, and once again, by the same logic, the capacitor starts charging, and the charging process being instantaneous because of this very small time constant, the capacitor voltage will once again simply follow the input voltage, like that. At this point, again the input voltage becomes lower than the capacitor voltage, and the capacitor voltage becomes constant. So this circuit is actually detecting the peak of the input voltage, one peak here, another peak here. So the capacitor voltage becomes constant, and the constant value is the peak of the input waveform, the last peak of the input waveform. That's why this circuit is called the peak detector. And the circuit file is available. You can run this simulation and look at these results. Let us consider the same circuit once again, but with a more realistic diode model with V on equal to 0.7 volts and otherwise ideal, that is with R on equal to 0 and R off equal to infinity. So these are the equivalent circuits. When the diode is conducting, we replace it with a battery or a voltage source V on, that is 0.7 volts, in series with R on. And when the diode is not conducting, we replace it with R off, a large resistance. What is the condition for the diode to conduct? Its P end, the voltage at its P end must be greater than the voltage at its N end by V on, or 0.7 volts. That means Vs must be greater than Vc by 0.7 volts. and that is what it says here. Vs must be greater than Vc plus V on. And in that case, this equivalent circuit applies. And as seen from the capacitor, the Thevenin resistance is R on, and therefore the time constant is R on times C. And as we have seen before, this is a very small time because R on is a very small resistance, ideally 0. And if Vs is less than Vc plus V on, then the diode does not conduct, and we have then this circuit representing the original circuit, and tau is R off times C, and since R off is very large, ideally infinite, tau is infinite. Let us start at t equal to 0. We have the capacitor voltage equal to 0 and the input voltage also equal to 0. And now the input voltage starts rising. But unless the input voltage becomes equal to 0.7 volts, the diode cannot conduct, and therefore the capacitor voltage remains at 0 volts. So let us see that part of the plot there. So that is this part here. And now when Vi or Vs becomes 0.7 volts, at that time the capacitor voltage would simply follow the input voltage. Why? Because the time constant for that process is very small, ideally 0. But it will follow the input voltage with a difference of 0.7 volts because this voltage here is not Vs but Vs minus V on, and that is this straight line here. What happens after this? After this, the input voltage starts decreasing, and the difference between this end and that end, which is Vd, becomes less than 0.7 volts, and therefore the capacitor voltage cannot change. We are now in this situation and becomes a constant. At this time, the difference between Vs and the output voltage Vc becomes 0.7 volts, and the diode once again starts conducting. We have this equivalent circuit, and once again the capacitor voltage starts following the input voltage with a difference of V on, like that. Now at this point, the input voltage Vs starts decreasing, and therefore Vd becomes less than 0.7 volts. The diode stops conducting, and we have this situation, and there is no way the capacitor voltage can change anymore because the current here is 0, and that is what we have here. So the output voltage in this case is quite similar to our previous example where V on was 0, except for this difference between Vs and Vo. Let us look at another application, and that is called a clamper. We have an input voltage here going from minus Vm to plus Vm. For example, this could be minus 10 volts, this could be plus 10 volts, centered around 0 volts. When we pass this input voltage through this circuit called clamper, what we get at the output is a level shifted version of the input waveform. So this input waveform has got shifted up, and now the lowest value of this output voltage is 0 volts. In other words, the output voltage has got clamped at 0 volts, and that is why this circuit is called a clamper. So a clamper circuit provides a level shift, and note that the shape of the input signal is not altered. So if this is a sinusoid, this is also a sinusoid. If this is 20 volts peak to peak, this would also be 20 volts peak to peak, and so on. Okay. Now this shift that we are talking about could be positive or negative. In this circuit it has been positive because in our input voltage the lowest value was negative. Now the lowest value is 0 volts. Here is a clamper which provides a negative shift. So this is our input voltage as before, and now this entire waveform has got shifted down to give us the output voltage, and the output voltage is now clamped at 0 volts, but the level shift has been negative. Here is an implementation of the clamper circuit. Very simple, just a diode and a capacitor in series. And for simplicity, let us assume this ideal IV curve for the diode with V on equal to 0 volts, R on equal to 0, R off equal to infinity. The input voltage is shown here in blue. It's Vm sin omega t. Vm is 5 volts. So the input voltage goes from 5 to -5. And as we shall see, the output voltage is a clamped version of the input voltage. Let's understand the operation of this circuit now. What we will do is make a few observations first and then look at the implications of those observations. First, when D conducts, the capacitor charges instantaneously since R on is small. That means the time constant, which is R on times C, is small. And in this phase, Vd is 0. This voltage is 0 because we have V on equal to 0 volts. And what does it mean? That means Vc plus Vs should be equal to 0 because there is no voltage drop across the diode. And that tells us that Vc would be equal to minus Vs in this phase when the diode is conducting. Second observation, Vc can only increase. Note that Vc is marked as plus here and minus here. So the capacitor current is the same as the diode current. And since the diode current can only be positive, Vc can only increase. And that is because a decrease in Vc would require the diode to conduct in the reverse direction, which is not possible. Third observation, after Vc reaches its maximum value, which turns out to be Vm, and we will see that in the plot. After that point, it cannot change anymore. Why? Because it cannot decrease for this reason, and so it cannot change. We then have Vo of t equal to Vs of t plus Vc of t, and this is simply coming from KVL. Vo of t, let's go like this, Vo of t minus Vs of t minus Vc of t equal to 0. So therefore we have this equation. And now since Vc has become a constant, we can say that Vo of t is Vs of t plus that constant, and that constant turns out to be Vm, which is the amplitude of the input voltage. So what does it mean? It means that the output voltage is a shifted version of the input voltage, and the shift is given by this constant here, which is positive. So we have got a positive level shift in this case. At t equal to 0, the capacitor voltage is 0, and now the input voltage starts rising. Let us see what happens as a result of that. With Vc equal to 0, this Vd is the same as minus Vs because of these opposing polarities. Now if Vs becomes positive, that means Vd is becoming negative. Therefore the diode does not conduct. The current in the circuit is 0 and the capacitor voltage cannot change. So it remains at 0 volts. What about the output voltage? In this interval, the output voltage is the same as Vs because this capacitor voltage is 0 volts. And that is the situation up to this point here. The green curve here is the capacitor voltage. It has remained at 0, and the red one is the output voltage. And as we have seen, the output voltage and the input voltage are identical because the capacitor voltage is 0 up to this point. Now what happens? Now the input voltage becomes negative, so the N end of the diode is now negative with respect to the P end, and therefore the diode conducts. What happens when the diode conducts? We already have figured that out. So Vc becomes equal to minus Vs because of this negligibly small time constant of the circuit, and that is seen over here. So this is Vc, and that is equal to minus Vs. This is our Vs. So if Vs is going negative, Vc goes positive. What about the output voltage during this interval? Now the diode is conducting in this interval, and therefore there is no voltage drop across the diode, and the output voltage is 0, and that is what we see over here. And now we note that the highest value that Vc can acquire is the negative of the lowest value of Vs, the input voltage, and it has already achieved that. So if this is minus Vm equal to minus 5 volts, the capacitor voltage is plus Vm or plus 5 volts. So now the third point, after Vc reaches its maximum value Vm, it cannot change anymore because any change would now require the diode to conduct in the negative direction, which it cannot do, and so therefore the capacitor voltage now becomes constant, and then we have Vo of t equal to Vs of t plus Vm. Let us see that in the graph. Okay, so now the capacitor voltage has become a constant equal to plus Vm, and this is our level shifted output. So our input is from minus 5 to 5, and output is from 0 to 10 volts. So it is identical to the input except for a level shift of plus Vm. Before we leave this example, we should make a comment, and that is we are generally interested only in the steady state behavior of this circuit. So that means this part here, and we have really discussed all of this only to understand the circuit better, but in practice we really don't care about what exactly happens over there. And in fact, if you go to the lab and hook up this circuit and watch the waveforms on the oscilloscope, we will not even see this part, because by the time you connect everything, start your function generator and oscilloscope and so on, all the transients would have died out, and you will only see the steady state picture, and that is what we are also interested in. Let us now consider the same circuit, but with a more realistic diode model, that is with V on equal to 0.7 volts. And here are the capacitor voltage and output voltage waveforms, and we notice that they are qualitatively quite similar to what we saw in the last slide. So let's try to understand the small difference that we see between these plots and the previous ones. Once again, let's make a few observations, and then we will relate these observations to the actual plots. First, when D conducts, the capacitor charges instantaneously, and that is definitely true because our R on is still small, 0 ideally, and therefore the time constant is small, and that is no different from the last circuit we considered. And in this phase we can say that Vc plus Vs plus V on is equal to 0. That's simple KVL. Vc plus Vs plus Vd, which is V on, equal to 0. And that tells us that Vc must be equal to minus Vs minus V on. Second point, and once again it is similar to what we saw in the last slide. Vc can only increase, since a decrease in Vc would require the diode to conduct in the reverse direction, which is not possible. So therefore this voltage Vc can only go on increasing. Once it reaches a maximum value, it cannot change anymore. And that is the third point. After Vc reaches its maximum value, in this case, what is the maximum value? That depends on what is the minimum value of Vs here. What is the minimum value of Vs? The minimum value of Vs is minus Vm, which is minus 5 volts. So minus Vs is plus Vm at this instant, and therefore Vc reaches its maximum value, which is Vm minus V on, and after that it cannot change anymore. So we then have Vo equal to Vs plus Vc as before. Vo is Vs plus Vc, and that is Vs plus Vm minus V on. In the earlier slide we had Vo equal to Vs plus Vm, and this V on was not there. So that is really the only difference, and we observe that over here. So instead of reaching 10 volts, Vo reaches now 10 minus 0.7. So that is Vs of t plus 5 minus 0.7. So Vs of t plus 4.3, and since Vs of t has a maximum value of 5, we have 5 plus 4.3, which is 9.3 volts. And in this case, Vo gets clamped at minus 0.7 volts, as we can see in this plot here. So the lowest value of Vo in the earlier case was 0 volts, and now it is minus V on, which is minus 0.7 volts. To conclude, we have looked at two new diode applications in this lecture: peak detector and Glamper. We have seen that the analysis of these circuits is very different from the diode circuits we have seen earlier, and therefore they have added a new dimension to our understanding. That is all for now. See you in the next class.